All right, so what I wanted to do was today, let's just go over all that, so that I would like to know what is it that you have done so far in 311. All right, so before I start with some new topics, so let me start with what is it that you guys already know. We just had a midsem, although a week back. So you have gone over the entire contents of our discussion that took place. So where do we start? 311, right? Introduction to, well, we call it what? Microelectronics 2, right? But it's really microelectronics 2, but it's introduction to semiconductors. The word introduction is important. It's really an introduction. Introduction to this semiconductor devices. All right, the word introduction is important. So where do we start? Where does the discussion related to semiconductor devices start with? What is the objective? What is the broad objective of this course? It's an introduction to semiconductor devices, fine, but at the end, once the course is over, what would happen? What would happen? In the sense that, what is it that you would know at the end of the course? How different devices function? Well, to some extent, the devices that we take up in this particular course are typically is a diode, is a BJT, depending on the time, and is the MOSFET. These are the three devices that we take up, right? Diode, BJT, and MOSFET. There are many other devices, but these are the three devices that we take up. To some extent, you already know how these devices work. You know what a diode is. You know what a BJT is. You know what a MOSFET is. So what are you looking for from this particular course? Diode, BJT, MOSFET, all of these things. What more is there to know about a diode? You know, what is it that you know about a diode? What do you remember about a diode? Does everybody remember this? Right? This diode equation tells us how the diode behaves with an exponential forward bias characteristics, and in reverse bias is more or less independent of voltage. So what do you want to know? We already have a diode equation. What more do you want to know about a diode?
What would IS and VT depend on?
IS. So you would like to know, what is this IS? Okay, what is this IS? And VT. VT is the KT by Q, right? KT by Q, okay. KT by Q, all right. So that's the only interest, to know what is IS. If I give you an expression for IS, that's the end. How we arrive at this equation, right? So you would like to know, where do we get it from, right? So you're looking for a derivation. You're looking for a derivation of this equation, all right? Okay, what will you do with the derivation? Suppose you know how to derive it. There'll be 10, 15 step particular process, and you derive this particular equation. Nobody's going to ask you to derive it again and again. So what is the point in deriving? Underlying assumptions of this model. Okay, so what you're saying is, as you derive, you're right, as you derive, you will know the assumptions of this particular model, correct? You'll know the assumptions of this particular model. Fine, that's, as you go through the process of derivation, you'll see that you'll have to make a series of approximations to arrive at this particular equation. Okay, fine, you'll understand that. What will you do with that understanding? I'll keep on asking that. What will you do with it? Okay, so you do a derivation. What do you do with a derivation?
You know what is the range or what is the...
Fine, assumptions. Important point is, once you understand assumptions, every model has a range of validity. Every model. There's nothing that is perfect, so it has a range of validity. There's a range over which the model is valid, and there's a range over which it is not valid. Right? So as you derive, as you know the assumptions, you'll know how to use this particular model. Right? So one is that the model of a diode that you need, eventually you would like to, diode by itself is interesting, but is more interesting in a circuit when you use it with other resistors and other kinds of things. And therefore, in order to understand those circuits, you need to understand the diode. And in order to understand the diode, you need a model. And under what condition you can use which model and all that, those are important aspects. But those are things that we can state for you. Range of validity, I can state, is in this range, this particular model is valid. Why do you need to derive it?
We want to operate in a different range.
I'll tell you the different ranges in which the operation of a diode takes place.
But you need to know as well.
Huh?
But you need to know as well.
You need to know, these are there in books, right? So I can state those things here. I can state those things here. So the question is, why do you need a derivation? I can state the model with all its assumptions, with all its range of validity, all of those things I can state it for you. Why do you want to know where does it come from? What you're saying is, I would like to know how it came about. Why is that of interest?
We can use that for deriving for other materials or semiconductors.
All right, so he's saying that, well, this derivation that is there, I would like to know, let's see. So I would like to know the derivation. All right. Derivation, maybe, I guess what you're saying is, it's a part of learning process, right? Learning process of how to analyze semiconductor devices, how to derive these things, so that if you came up with a new diode and you want to know how that new diode works, then maybe what I learned through this particular analysis, I can apply it there. Right? So the point that I'm trying to emphasize is that there are, so it's a learning process, of course, learning to basically analyze. Learning to analyze a device, a semiconductor device. So the point that I'm trying to emphasize is that there are two perspectives. One is, there's a perspective from if you look at a diode, there's one perspective, which is the perspective of somebody who would like to use a diode. A diode is given and you would like to use it, which is a circuit perspective. There's a circuit perspective where the chief concern is, how do I use a diode properly? How do I use it effectively, properly? Right? So there's a circuit perspective. For that, you don't need any derivation. All you need is a statement. This is what my diode is. This is its model. These are the range of validity, and these are its limitations and things like that. What you need to know is the diode from an external point of view. If I have a diode like this, I would like to know a diode from an external point of view, from basically a IV characteristics kind of a view. That's from a circuit perspective. But if you're a device engineer, if you're a circuit engineer, fine. So whatever you learned in 210 and other things, the way to look upon a diode, that's fine. You can go ahead with that and this thing. But if you're a device perspective, if you look at it from a device perspective, then You're not happy with just that. You would like to know how it came about. Because you would like to analyze not a diode circuit, you would like to analyze the diode itself. Let's say if tomorrow, as somebody pointed out, tomorrow somebody makes a change in the diode. Normal diodes are, for example, normal diodes, as all of you know, is a, let's say, normal means the common diode is a P and N. And let's say this is made up of silicon and this is made up of silicon, right? Both are made up of silicon, P and N type. What if somebody says the following? Say we ask a question that, fine, this P I make of silicon and N I make of germanium. It's no longer a conventional diode now, because a conventional diode is both materials are the same. You know, germanium has a different band gap. Silicon has a different band gap. And so what happens now? Does it still behave in the same manner? I mean, are there changes? So you would like to know. So this is what a device engineer would like to know. What would happen if I just replace and make N-type out of germanium? Are there benefits? Are there some benefits of doing that? Are there some drawbacks? You know, we would like to know all these things that are there, right? So what you are interested, you know, in this particular course, we are looking at from not from an external perspective. We would like to go inside the device and understand how these things come about, how these characteristics that we already are familiar with, how do they come about, so that as we learn to analyze these particular diodes, we can then maybe perhaps handle new devices and maybe come up with new structures. And so those are the issues there as a device engineer. So where does the journey start? So if you'd like to understand a device from a device perspective, where do you begin with? What are the key concepts? Where do you begin with? Important concepts that you've gone through. If I want to understand a semiconductor device, obviously I need to understand a semiconductor itself, a simple piece of semiconductor. Before you can understand a PN junction or a PNP or a MOSFET and all of that more complicated things, you would like to understand a semiconductor. So the understanding of a semiconductor, what is it built on? What are the key concepts? What are the key concepts that are there? Understanding of semiconductor. I mean, whatever comes into your mind may not be in a nice logical manner that I need to start with this. What comes into your mind? If I would like to understand a semiconductor, what are the elements of it? For example, without without those essential elements, I cannot meaningfully talk about a semiconductor. Huh? So what he's saying is band model of semiconductors. Band model of semiconductor. The lattice structure basically leads to this. Lattice structure that you see, yeah, these are crystalline solids. What we are talking about is crystalline semiconductors. By the way, all semiconductors are not crystalline. We are only in this case talking about crystalline semiconductors. So the lattice structure we start with. And the lattice structure, for example, you've already read about lattice structure, right? A little bit about that. It says silicon is a diamond lattice. What do you get out of that? Fine, silicon is a diamond lattice. So what do I do with it? So what? It's not a simple cubic lattice. It's not a face-centered cubic. Maybe it's a diamond kind of a lattice. What do I do with that knowledge? Fine, it is a diamond-centered. Okay, diamond lattice. What do I do with it? What implications does, whether it's a diamond lattice or a cubic lattice or a trigonal lattice or whatever, what implications does it have? Huh? So, depending on the crystalline structure, of course, the band nature of these particular solids would change. The band nature of that particular solid would change here. Right. So, anyway, so from the band model of semiconductor, what are you getting? All right. So what do you mean by saying there are bands in the semiconductor?
Equations for number of electrons and holes, conductivity, etc.
No. What do you mean by that? If I need to understand a semiconductor, I need to think of semiconductor in terms of bands. What do I mean by that? What do I mean by that? Band view of semiconductors. What does it mean? That in my semiconductor that there are electrons exist in bands of energy, right? Right? So we say, well, there's a series of bands. There is a series of bands. I mean, this is a very simplified picture. There are all series of bands that are there. We know that in an atom we have discrete levels, 1s, 2s, 2p, 3s and all that. Those things, when you bring it together in a crystalline form, you get all these bands. All these bands that are there. Right? These bands of energies. Okay, fine, there are bands of energies. What do I do with that? Fine. I mean, just like an atom has all these discrete levels, a solid has a series of bands, bands of energy levels. Okay, what do I do with it? What do I do with that? Okay, so what?
See how the bands are filled.
See how, naturally, there are lots of electrons in my system, and these electrons are occupying these particular bands. Just like they fill up 1s, 2s, and 2p, they fill up these bands here. So there would be a band which is full of electrons, there's a band full of electrons, all these things are there, fine. They fill it up, okay, then?
So we know that at various conditions what amount of electrons you have in various bands.
So the one thing that we know is that they have these semiconductors, they have a picture like this, that they have a series of bands which are full, and then there's a band which is empty. All that you see is completely full bands and completely empty band. And then we know that this is what we call this as the valence band, and this is that we call as the conduction band. And we ignore all of these. We ignore all of these bands. Why?
Because their electrons are not conducting, so and they will not they cannot be excited to the conduction band also.
So if I take this particular, you see, a band full of electrons, right? We are saying completely full of electrons, and we are ignoring it. We are ignoring it. We are saying there are a huge number of electrons, and we are saying, well, it doesn't really matter.
They are not
mobile. So this thing, please clarify this, that this is an important point. A full band does not contribute to conduction. Does not contribute to conduction. So there are lots of electrons that are there. They are useless. As far as electrical properties are concerned, they play no role. All these bands that are there, huge number of electrons, they play no role. That's why the focus shifts to the valence band and the conduction band. And the valence band, and so we know qualitatively, if conduction has to take place, which means that you apply an electric field, let's say, and the electron has to accelerate opposite to the direction of the field. Acceleration means it has to take up energy from the field. Where will it go? These electrons that are there, there's no place to go. And we'll not go into the details. If you go and look into the band here, for every electron that is moving right, there's an electron moving left, so they all cancel each other. It's not that the electrons are not moving in these bands. The electrons are moving, but they all cancel each other. Okay. So the focus is on the valence band and the conduction band, because at typical, room temperature and all that, what happens is valence band gets a little bit empty, and you start getting the electrons in the conduction band. So conduction band doesn't remain at a room temperature. Conduction band doesn't remain completely empty. There are few electrons there, and valence band becomes empty, partially empty. So both bands are partially empty, and then these bands can contribute to current conduction. So we shift our attention to, we start drawing a EC denoting the bottom of the conduction band, and we start drawing EV denoting the bottom of the valence band. and then the gap becomes of importance. Of course, when we draw EC and EV, we know that there are lots of levels above EC. And similarly, we draw EV, we know that there are lots of levels. We are only drawing the band edges. Fine, so what do we do next? So we know that there are bands in semiconductors. The bands which are of interest are the valence band and the conduction band. And there's a gap between them, between the valence band and the conduction band. What is next? What is next? So where do we go from here? Okay, so we have EC, EV, and we have EG. Where do we go from this point? So all right. So what you're saying is we would like to understand how many electrons. We are saying that conduction band will be partially occupied, and valence band will be partially occupied. So out of the band theory one, before that, a very interesting concept comes in, that the valence band that you see here, if I were to draw the valence band, we are saying valence band is like 99% full. What percentage will it be full, by the way? What do you think is typically, in hindsight, we know how many electrons are there in conduction band? If you take a pure silicon, how many electrons are there? Even though we have not, we've done the calculation, but if you recall, how many electrons are there in the conduction band? Roughly? Intrinsic silicon? 10 to the power 10. 10 to the power 10. Okay. How many electrons do you think are a rough order in the valence band? 10 to the power 22. So if we are talking about the vacant states and all that, if we talk about a vacant state here, how many vacant states are there? So what percentage is it full? You can imagine 10 to the power 22 and 10 to the power 10. So how full is it? 99.9999, you can just, right? It's just 99.999, because all that you have is that few number of vacant states. So one of the interesting things from here, if you look at the band structure, is that all these electrons are there now. There are how many electrons are there? Well, roughly of the order of 10 power 22, because the missing electrons are only 10 to the power 10. So roughly you have 10 to the power 22 electrons. So one of the insights that comes from band theory is that when you apply a field now, those 10 to the power 22 electrons are going to move, because it's now partially filled. They're going to move. But the movement of those 10 to the power 22 electrons and the current contribution can be modeled in terms of the vacant states. So the concept of a hole, that all these electrons that are there completely, in the valence band, their movement. So if I were to look at these electrons, if I were to look at these electrons and I were to write, current carried by these electrons here, J equal to Q, let's say total number of electrons in the valence band, NV, some mobility, let's say an electric field and kind of a thing. This whole thing we are saying can be modeled not in terms of number of electrons, what these electrons, but we can model it in terms of P mu P E. So instead of talking about all those electrons in the valence band moving and contributing to current, we are saying it's the same thing as if you talk about the missing electrons that are there, associate a mobility with that, and the current carried by these here is the same as current carried by these. So that's one of the insights of, it comes about from the band theory. So the valence band can be, current conduction in valence band can be modeled in terms of the holes that are there. All right. So one of them is that a full band does not contribute to current. So three things. One is you have a band structure. Electrons occupy bands. Second thing is a full band does not contribute to conduction. The third thing is the valence band that you see here. All these electrons that are there, their conduction can be modeled in terms of holes. So we have now, so it tells us that in semiconductors, if I want to talk about electrons, I want to talk about conduction, I have to talk about electrons. By electrons, we mean now, remember, electrons in conduction band. And we talk about holes. Holes in valence band, referring to V for valence band and electrons in conduction band. These are the two things that I have to understand. How many electrons are there in conduction band? How many holes are there in valence band? I need to know those things in order to say how much current flows. Okay? So then that brings us to how much current flows. So that brings us to, how do I know the number of electrons? So when we write n, we always mean n in the conduction band, right? So the issue is, how do I calculate number of electrons in the conduction band? All right, so that is of interest. How many electrons are there? And as you may imagine, in all of these places, whenever you want to understand something, you want to understand something first of all in its simple form, and then gradually add complexity to it. Okay, so what we do is we start with the situation equilibrium. We start with the situation of equilibrium. No voltage is applied, simple semiconductor, no light, no voltages, nothing. It's a piece of semiconductor just sitting there, and we would like to know how many electrons are there. And so then we put equilibrium, we put N0, denoting that it's an equilibrium. So that's the simplest problem. If I can't solve this simple problem, N0, how many electrons are there in equilibrium, then I have no hope of solving how many electrons are there when I've applied a voltage or when I shine light on it. So in some sense, we start our analysis with the simplest problem that we can have is, if I have a piece of semiconductor, no doping, nothing in it, no impurities, pure piece of semiconductor, how many electrons are there in that particular one? So with that, you know that then the band picture tells us is, if you have a band like this, you have a conduction band like, you have an EC here and your EV here. So, so you know that we say N0, we know that there are states, a lot of states here. So N0 is equal to, we introduce the concept of density of states. How many states are there? Density of states multiplied by what is the probability that these electrons are occupied, and we integrate from EC to infinity. So band theory gives you this. Again, looking at the bands, we arrive at an expression for GE. And this is the Fermi-Dirac, tells you the 1 plus e to the power e. So we introduce a new concept of Fermi energy. The probability of occupation is given by Fe. So EF is a new level that comes into being. So far we had only EC, we had EV, we had EG, we had all these levels that are there, and now another level comes in, which is EF. And out of that, after making your assumptions that Fe this can be approximated by a e to the power minus E minus EF by KT, we arrive at this expression. N0 is NC e to the power minus EC minus EF by KT. We arrive these expressions here. P0 is whatever, NV minus EF minus EV by KT. We arrive at these expressions. How many electrons? We are able to now predict how many electrons are there in the conduction band, how many electrons are there in the valence band, and it also tells us that N0, if I have intrinsic, then N0 is P0 equal to Ni, and Ni, and we get this. Ni is Nc Nv e to the power minus Eg to KT. So it tells us even a value. We are even able to calculate that if I have a piece of silicon, how many electrons are going to be there in that piece of silicon. I mean, that's amazing if you think about it. Given a semiconductor, now I can say, well, this semiconductor is going to have this many electrons that are there, and this semiconductor is going to have that many electrons. We are also able to predict that the carrier concentration that is there will go exponentially with temperature. So there are things that we can predict about a semiconductor, which we can measure. And check whether the predictions are correct or not. So that's something interesting. So N0, P0. All right, so we get this from a band theory. What else? Where do we go from here? And we can introduce the concept of N0 is Ni. We can write it in terms of e to the power EF minus EI. All those things, different things that we can write, right? P0 we can write. And we also get N0, P0 is Ni square. All these things that we get. Okay, where do we go from here? Fine, band theory. We got all this. Where do we go? Okay, what is next?
Doping.
All right, so we can dope. We can take a pure semiconductor is not of that interest. So we can dope, we can add an ND here, we can add an Na here, we can dope it, fine. What is the insight from doping? Okay, so you add an impurity. You add a group 5 impurity, group 5, or you add a group 3 impurity to make it p-type or n-type. So you have achieved some control over your semiconductor. You can increase now the number of electrons and make it much larger than number of holes, or you can make the number of holes much larger than number of electrons. So you're achieving some control over your semiconductor. I can add impurities and alter the amount of electrons, amount of holes, fine. Doping is important. Ability to alter. Okay, doping. What other things from doping do you get? How do you understand doping? So when you need to understand doping, it's not just a group 5 and a group 3. It's not just a group 5 and a group 3 element. There's something more in so if you want to understand doping in more detail, then we know that, well, so remember we had EC, we had EF, EV, and we had, let's say, EF. And when you add doping, we said, well, doping manifests itself as a level, ED in my band diagram, a donor level. And different impurities are at a different energy. And this EC minus ED is important. This EC minus ED is important. Unless this energy difference is small, my material, I can add a element, but if EC minus ED is not small, I will not get ionization. So if it's not just the doping, but you're looking for Nd plus, and you're looking for Na minus. You're looking for ionization of donors. You're looking for ionization of acceptors. Then only you'll get those electrons and holes. So EC minus ED and all those things that are there, there are implications of it. How many donors I can add and still get ionization. So ionization is important. It is temperature dependent. So ionization of this is important. And this depends not only on temperature, but depends on, as we discussed in one of the lectures, it depends on NC and NV. And depends on this EC minus ED. So EC minus ED, temperature, NC, NV, these all decide whether my donors are ionized or not. Okay, so that part is there. Okay, so doping is there. What else? Doping is one important. We can alter the amount of electrons and holes in the semiconductor. What else? So you know the number of electrons that are there in your system. Electrons, holes, how you can alter with doping. Then what is next? Disturbing the equilibrium. So that's all you would like to know about equilibrium? You know N0, P0. What else is there in equilibrium? No current is flowing, nothing else is happening. No voltage, no light, nothing. Right? You have only N0 and P0. Right? So you know about equilibrium. So the next thing that he says, okay, disturb the equilibrium. And the way we disturb the equilibrium is we apply a voltage. That's the most common way of operating a semiconductor device. A diode, you apply a voltage. BJT, MOSFET, all of these things, you'll apply a voltage. And one of the things that happens, obviously, is when you apply a voltage, you get a current. You get a current. And so now you would like to understand how does this current flow here. And so out of that we got current, there is a drift process and there is a diffusion process. There's a diffusion process. And drift process, we understood Jn is Qn, mu n for electrons E, and this is J n drift, and Jn diffusion was Q dn by dx. So it traces that there is a drift current and there is a diffusion current. And if I would like to understand drift current, it raises, I need to know the mobility. I need to know the diffusion constants. And so mobility, we did an analysis of mobility. We said, well, mobility can be written as Q tau by m. Mobility depends on scattering, how scattering takes place. Mobility depends on effective mass and all of those other things. Not only that, this whole product is a drift velocity. And although we didn't discuss it, we said if you look at, which we have to do at some point, if you plot drift velocity, well, it goes linearly, but eventually it saturates also. It increases, but eventually it saturates also. So if you are in this region here, well, you can write as mu and E. But then it doesn't remain linear always. So we need to understand a little bit more, although we went and looked at mobility, how this term Q tau by M and all that comes about. But we need to understand why it saturates and all that, little bit on that. And we also said diffusion constant is mobility times kT by Q, the Einstein's relationship. That's the other thing that we got. And the same equation holds for holes also. Fine, so we have now Jn and we have Jp. Fine. Where do we go from here? We have expressions. Jn expression and we have Jp expression. We know it has a drift component, it has a diffusion component. Where do we go from here? These are the two ways in which current flow, drift and diffusion. Do we have all the information now? Where do we go from here?
Conductivity.
Conductivity comes in from here. Jn is Q, and when I write Jn is Q and mu and E, conductivity comes from there. So now what happens is, these equations are there. You need, besides these, a few other equations in order to, equations which are valid everywhere. One is, all of you know Gauss's law, right? What does Gauss' law says? Del dot D equal to rho, right? And let's just write it in one dimension. It says del E by del X in one dimension is rho by epsilon, assuming epsilon is independent of this thing. Del E by del X is rho by epsilon. Rho, please remember, is coulombs per, if I use centimeter cube, is volume charge density. Volume charge density. So that's one equation. Is this equation relevant to us? Will it be helpful? I mean, Gauss's law, of course, is very general, applicable at all places. Will this equation be helpful for us? Because remember, drift current and all that, what does it depend on? Electric field. And do I have charges inside my semiconductor? I have electrons, I have holes, I have ionized donors, ionized acceptors, I have rho. And how are these? So obviously this equation will be very important for us. Okay? Del E by del X is very important for us. Normally what we do is we write E equal to minus del psi by del X. And so we write this equation as del square psi del X square equal to minus rho by epsilon. And we call this the Poisson's equation. So it is one of the central equations because we have charges inside a semiconductor. And what are rho? Can we write down rho? What will rho be equal to? What are the charges inside my semiconductor? Rho equal to Q multiplied by what else? What are the positive charges that I can get in my semiconductor? Huh? Nd plus. All ionized donor atoms will give me a positive charge, and holes will also give me positive charge. And where do negative charges come from? N electrons, and if I have Na minus. So this is general. So rho is Q. In some region I may have Nd, in some region I may have Na minus. Maybe I have both of them. Maybe I have none of them. I don't have Nd, I don't have Na. That's a general expression for this thing. So Gauss's law or Poisson's equation is obviously very important for us because it's relating electric field and charge. That's very important. The other equation which is very important for me is what we call as the, see if this makes sense, continuity equation. Continuity equation. Continuity equation, what it is saying is basically a continuity equation is basically a particle conservation equation. Particle conservation equation. What do I mean by that? Well, take a small volume here, small region of a semiconductor. And the question that we are asking is, what is the rate of change of, let me put it instead of, let's write down for holes. So let's say, what is the rate of change of hole density in this region here? Let's say this is of delta x. Change of hole density in a small region. Why would a hole density change, by the way? What are the processes that can contribute to, if I take a small piece of semiconductor and ask, why would the hole density change in that? What are the reasons? What reasons can you think of?
Current.
Well, so you're right. So one way you can say is, let's say this is JP and this is JP x plus delta x, right? So what you're saying is, if JP x plus delta x is different from JPX, more charge is going in and less charge is coming out. Can I write this as, note that this is P. Note that can this point be written as 1 over Q del JP by del X minus rate of increase of hole density in this region can be written as minus 1 over Q del JP by del X. Can I write like this? Think about what is JP. JP is number of holes which are coming out. This is JP, number of holes which are going in. And can you write it like this? So I'll leave it up to you. Please see that you can write like this. What else can happen? What else can happen? So more holes are coming in, and let's say less holes are going out, so the holes are accumulating in my region here, right? Okay. What else can happen? Why would number of holes change in that particular region? Well, in semiconductors, there's always a process of generation. Right? Remember when we drew EC and EV? EC and EV, where did these electrons come from? Through a thermal generation process. The electrons from here went here, and you ended up with an electron and a hole. There is a generation process always going on. And on top of that, you can have light and other things that are there. So we need to add a generation rate. Generation rate of holes. There's a generation which is happening, which is calling it GP. And then if this is happening, a reverse process is also happening, which we call as a recombination. Right? So we are saying that the rate of change of hole density in any region is equal to due to the current, any change in current. If the current is changing with X, then I will have holes accumulating or holes decreasing. That will happen. Or generation rate or recombination rate. These are the birth of the electrons, this is the death of whatever holes, and this is what comes about because of the flux, any change in flux. So that's the continuity equation. So that is also important because it tells us how hole density or electron density may change with time. And we can write this down. We can write del N by del T. Now because electrons carry negative charge, so we will put 1 over Q del Jn by del X plus Gn minus Rn. Now in most cases when you generate a hole, you also generate an electron. And when you recombine a hole, you recombine an electron. So these rates are actually the same. So you can just call a G and an R. You don't need to say Gn and Gp, Rn and Rp. You can just call them as G and R. So obviously now you would know how do these things recombine. Generation is fine. Generation is, let's say, thermal or light and all that. How do electrons and holes recombine? How do I think of recombination? Right? So we need to understand this. How does a recombination take place? Generation is fine. There's a photon comes in, interacts with the lattice, and you end up getting an electron and a hole pair. Or it acquires energy from the heat and an electron and a hole pair. This thing. So you need to know what is the generation rate. What is the rate at which the carriers are generated? Fine. But if I apply, look at this equation. Look at this equation. If I apply this equation at equilibrium, what does it mean? So continuity equation is very general. If I apply it at equilibrium, what will be del P by del T? What will it be? 0. Nothing is changing with time. Is there any current flowing into equilibrium? 0. What does it mean then? G minus R must be equal to 0. What it says is G minus R equal to 0. Which means that this is actually a dynamic equilibrium. Carriers are continuously being generated and they're recombining. Okay, so we have a continuous process here. We have a continuous process, as I said, you have a generation rate which is happening and you have a recombination which is continuously happening, and the two balance together, G equal to R. At equilibrium, the two are balanced with each other. All right, so if we look at it, now we have all these equations. We have this current equation, Jn is Qn, let me write it Qn mu n E plus Q dn by dx. Similarly, we have an expression for Jp, and we have Poisson's equation, del square psi, del x square minus rho by epsilon, and we have this continuity equation now, del P by del T minus 1 over Q del Jp by del x plus G minus R. We have all these equations now. Plus we have all these n equal to nc and all that equation that we just said, all this. We had mobility, mu n we understand, we had dn by mu n, kt by q. We have all these equations that are there. These are all that you see here. These are what we call as the semiconductor equations. These are all the semiconductor equations. For most of the problems, these are all the equations that you need to know. Current expressions for current, drift diffusion currents, Poisson's equation, continuity equation. Along with those other things, n equal to nc, p equal to nv, mobility, diffusion constants, and things like that. One more thing we need to do is we need to understand this R. How do things recombine? We need a model for R. Okay? Generation rate, as I said, depends on the external agency. Whatever is causing generation, it depends on that. So we need to understand R. So now all these equations that you have, now given all of these equations, note that these are all differential equations. These are all differential equations. So now if I take a piece of semiconductor, whatever device you take, and if you give this may be complicated device, and if you give the boundary conditions, if I give the boundary condition, let's say I'm applying a voltage equal to 5 volt here and putting it to ground. 5 volt at one end and putting it to ground the other end, I give you the boundary conditions, right? And I also tell boundary conditions will come, well, these are ideal contacts and all that we specify here. So what I'm saying is we specify the boundary conditions. We specify the boundary conditions and you have all the equations with you, all the semiconductor equations that are there. What do you have to do? These are a set of mathematical equations, differential equation, boundary conditions are given to you, you solve it, what will you get? You'll get your IV. You'll get your IV characteristics. So one way of analyzing a semiconductor device is all the equations are given to you, boundary conditions are given to you, it becomes a mathematical problem. And what are those equations? If you go back and look at it, the equations are partial differential equations, because it's a function of t, is a function of x. Well, if you're doing steady state characteristics, then all the time derivatives will go out. You'll get a set of differential equations, and you have a boundary condition, solve it, and you get your IV characteristics, current versus voltage. And this is the approach that is taken in a simulator, a device simulator. Just like circuit simulator you guys are familiar with, we have device simulators. All those device simulators do is all these equations are given there, and you specify how much voltage is at the ends and all that. They will take these equations and numerically solve them. Numerically solve them. Numerically solve all these, numerically solve the equations. So I've given you all the equations today, at least for most of these devices, PN junction, bipolar and all that. They can all be analyzed with those equations. So in a way, you have a complete set of equations now. Mobility is there. I need to tell you about recombination. How does recombination occur? If I give you an expression for recombination, let's say R equal to whatever, some expression in terms of N and P, then the whole thing is complete with the boundary conditions. Discretize the equations, you get a matrix, solve it and all that, and you get your idea. That's how a device simulator will work. It will give you an idea, right? For a diode, if I do that, it will give me all of this here. It will give me all of this. But that's not the approach that we would like to take. As I said, our goal is to get analytical model. We are not looking for a IV graph, simply. We are looking for an analytical model. So we want to take these equations and symbolically, right, a symbolic analysis of all those equations and derive a closed form expression. And as we go through that and we arrive at it, see, numerically will not give you any insight. It's just a bunch of equations, discretize it, and you'll get a graph. Same thing you will ask, how did that graph come about? Just like you do an experiment and you get a graph, I versus V, simulator will also give you a graph. And you'll say, where did this come from? The advantage of a simulator, of course, is that you can go and say, what does electron density look like inside my semiconductor? Where is the Fermi energy? You can ask all of those questions which you can't do through an experiment. No experiment will tell you where EF is, right? But in a simulator, you can plot EF, you can plot EC, you can plot mobility, you can plot all the things that are there. So simulator can help you understand. Simulator can be a great tool for understanding because you know what is happening inside it. It gives you a picture of P, N, electric field, all of those things it will give it to you, right? But so what we are looking for is now a way to solve those particular equations, go systematically and solve those equations and arrive at the closed form analytical expressions for, let's say, current in a PN junction and capacitance in a PN junction and things like that, right? So I've given you all the equations. The focus then will shift to us, how do I apply those equations? Okay, starting from simple problems and going towards more complex problems. How do we apply that? Okay. Before that, I need to talk about briefly about this R here, how recombination takes place. Okay? All right, so let's stop here.